Hey everyone, welcome. If you've ever felt that stomach-dropping, thrilling rush on a roller coaster, you've actually experienced some seriously complex physics. But today, we're going to look at the elegant mathematics that can describe that entire ride with perfect precision. So yeah, buckle up.
Really think about it for a second. It's not just about how fast you're going, right? We're talking about capturing the feeling of every single bank, every sharp curve, and every spiraling corkscrew. So, how do we even begin to build a language that can describe that kind of motion through space? And that question, that's exactly what we're going to call the roller coaster problem. Our whole goal here is to create a complete mathematical snapshot of that coaster car's motion at any single instant. Okay, so to really get what the ride feels like, a speedometer just won't cut it. We need to know three things. First, which way is the car pointing? Second, how sharply is it turning? And third, how much is the track itself twisting or banking? Let's build this whole thing up, piece by piece. So first things first, we're going to start with the absolute basics. To build our mathematical picture, we'll begin with the two most fundamental parts of moving along a curve: which way you're going and how you're turning. Imagine you're in the front seat of the coaster. And freeze. We pause time at one specific point on the track. The most basic question we can ask is just, which way are we heading right now? So in the world of math, this has a name. It's called the tangent vector, and we'll just call it t. And honestly, the best way to picture it is to think of the beams from the coaster's headlights. They always point straight ahead, exactly in the direction of motion, just for that one split second. Easy enough, right? Okay, but hold on. We all know a roller coaster is way more than just moving forward. What about that feeling, The one that shoves you to the side when you hit a sharp curve. That force isn't pointing forward, is it? No, it's pulling you inward. And that feeling, that inward pull, that's our second piece. It's called the normal vector, or n. This is an arrow that always points directly toward the center of the curve you're on. So the sharper the turn, the more you feel that normal vector's influence. It's basically the math behind the g-force you're feeling. All right, so now we've got our forward direction, t, and our inward turn, n. With just these two, we can perfectly describe any motion on a flat plane, like a car on a racetrack. But come on, roller coasters aren't flat, are they? They dip and climb and bank all over the place. They live in 3 dimensions. We're still missing something. All right, it's time to go 3D. This is where we add the final piece to our little moving frame of reference, the thing that will let us capture the full picture of the ride. And this new piece is called the binormal vector, or B for short. Now this is an arrow that sticks straight out, perpendicular to both our forward direction, t, and our inward turn, n. The easiest way to think about it is an arrow pointing straight up from the floor of the coaster car. It tells us exactly how the track is tilted at that very moment. And there you have it. That's our complete set. At any point on that track, these 3 vectors move with the coaster. You've got t for forward direction, n for the inward turn, and b for the upward tilt. And when you put them all together, t, n, and b, you get what mathematicians call the TNB frame. It gives us a perfect instantaneous snapshot of the coaster's orientation in space. But here's where it gets really interesting. Because this frame, this TNB thing, it's not standing still. It's moving and twisting with the coaster. And how it changes? Well, that's where the real magic happens. This brings us to the coolest part, torsion. So what is torsion? Well, it's basically just a number represented by the Greek letter tau that measures how fast our little frame is twisting around. Specifically, it's tracking the rotation of that binormal vector, B, the one showing the tilt. So if the track is banking like crazy, you've got high torsion. If it's staying flat, torsion is 0. It's literally a measure of the track's twistiness. And this is such a great way to picture the difference. Think of a classic old-school vertical loop. You go up, over, and down, but the whole thing stays in one flat vertical plane. The track never banks left or right. That's a perfect example of 0 torsion. But then you've got the corkscrew, right, where the track is just constantly twisting and spiraling. The car is twisting as it moves forward. That is high torsion in action. Okay, so you might be thinking, this is cool, but why does all this math matter? Well, it turns out this framework isn't just for designing theme park rides. It's a fundamental tool for describing pretty much any kind of motion you can imagine. This exact same math is the secret sauce behind so many things. Animators use it to create those smooth, sweeping, realistic camera movements in CGI movies.
Engineers use it to program the incredibly precise path of a robotic arm on an assembly line. Biologists even use it to model the complex coiling of a DNA molecule. And, yep, civil engineers use it to design the banking on highways and railways to make them safer for all of us.
And that's really the big idea here. This whole framework, the tangent, normal, and binormal vectors, plus the ideas of curvature and torsion, it gives us this incredibly powerful language. It lets us describe not just an object's position, but its entire dynamic orientation as it turns, tilts, and twists through our world.
So, here's something to think about. The next time you see a stunning CGI camera sweep in a film, or even just drive along a banked curve on the highway, take a moment. See if you can almost see those invisible vectors, that unseen math shaping everything around you. Thanks for joining me on this one.